All right. Sorry, I'm running behind a little bit. Let's get started. So last class, we talked about doing some kind of procedures for selection and regularization. Selection / regularization. Okay, so this included some kind of subset selection. So this is our forward and backward regression or stepwise selection. And then we also talked about some shrinkage methods or regularization methods. So this is bridge and lasso. Okay, so quick refresher, right? Whole idea here, maybe you want to figure out essentially if you have a data set that has a lot of variables, right? This is going to reduce the number of coefficients. And this is going to shrink unimportant coefficients. Okay, so different sort of methods that are kind of getting at the same thing or similar types of things. If you were to use this technique compared to this technique, right, maybe this will drop coefficients that are not so important, whereas this one are going to shrink them towards 0. Okay, so this is going to be maybe a little bit new or different for a lot of you, right? If you're used to doing linear regression, this gives you like different betas essentially. And both of these are going to be helping you deal with issues like overfitting, right? In this case, you have the AIC, BIC, adjusted R-squared criteria that's guiding you to the best model without having essentially too many variables. And shrinkage is going to be guiding you by penalizing your model if you have too many variables, essentially. We're going to finish off this section talking about a third technique. And this is known as dimension reduction. And so some examples of this. PCA, which stands for principal components analysis. And PCR, which is principal components regression. And similar in principle in terms of what we're trying to do here, reducing essentially the size of the model by identifying the sort of most important contributors. And this is actually going to transform your predictors. in a lot of ways, I think dimension reduction is kind of the most abstract, but we're gonna do our best to understand what's going on here. So dimension reduction. So I'm going to kind of write the sort of fundamental mathematics behind what's going on here. And then hold your thought. If you don't quite understand what's going on, we'll try and sort of visualize this as well. So we have something like Zm is equal to the sum of j Okay, so if you kind of just look at this for a second, this kind of looks like a linear regression, okay? Imagine if you just replace this this y or the z with a y. Instead of zm, you might have yi, right? And then here, instead of what is this Greek symbol? I always forget. Instead of this Greek symbol, you have a beta, right? So then you just have beta times x, okay? So kind of analogous. In a PCA, you're going to have something that looks like this, and we'll get back to this later. This kind of just indicates that you have a circle in each dimension. And again, when we get to the visualization of what's going on here, I think maybe this will make a little bit more sense. So we have linear combinations from x to z. And importantly, m is less than k. So if we think about in a linear regression, let's say you have a k number of variables, okay? Here, we're going to have an essentially represented m number, and it's going to be less than k. So if I were to do something like y equals beta 1 x1 plus beta 2 x2, and so on to beta k xk, the idea is to use dimension reduction to transform this, so I get something like this. Yi equals theta 0 plus the sum of m theta m z I m. Okay. So instead of doing y is equal to beta x1 plus beta x2 and so on and so forth, I'm going to modify my x's and I'm going to reduce the x's in some way, okay? And I'm going to make it so that instead of having k x's, I'm going to have MZs. I'm going to have a fewer number of parameters essentially that I'm going to train my Y on. And the whole idea is I'm going to try and take, quote unquote, the most important pieces of X to put into here. Let's suppose I have two variables. That looks something like this. So notice in this plot, this is not X and Y. These are going to be your X1 and X2. So I'm going to try and show what's happening in 2 dimensions here. You can imagine that the variation between these two guys are helping to explain some of the stuff that's happening in Y, okay? And what dimension reduction does is it leverages that variation. So essentially what I'm going to do is take a piece of this that sort of maximizes the variance, okay? So I basically want to be able to draw some kind of line through here, right, which turns out to be a linear piece of it. And the idea is that essentially if I draw kind of a circle around all of the points, which is essentially what this is doing, you are essentially taking the sort of longest line that you could get out of this circle, okay? And this would be known as your first component. And you are maximizing the variance. This way. There is another component that you can take that's always sort of orthogonal. So that would be something like this. And this is essentially what you would see in just 2 dimensions. Okay, you can imagine that if I had like an X3, this could be a cloud of points and you'd have some kind of like ovaloid kind of shape, in which case you would have possibly a third component that could be orthogonal to these 2, right? So this would be my second component. You could have a different graph. X1, X2, where your points might be, let's say, more spread out. and my first component would be still something like this, and maybe the second component would be larger here. So this would be first component, second component, and the kind of difference between my left-hand side and right-hand side is that here we're kind of more clearly able to say that the first component is a lot more important than the second component because it's capturing more relative amount of the variation between your x1 and x2, whereas here your components might be sort of similar in magnitude. So you might theoretically, okay, and we'll talk about a more strategic way of doing this, but sort of qualitatively looking at this, I might say, okay, just do one component for a PCA with this guy, but you might want to do both components for the guy on the right. The reason why it's always orthogonal is because your z's here have to be independent of each other. Okay, and so mathematically you'll always get something that kind of looks like this. So the basic idea of this technique is that because your m is always smaller than your k, right? You have fewer overall variables that you're going to end up looking at. That means that you're preventing overfitting because you're only essentially taking the most important parts of your x's. Okay. So let me hang on for a second and ask if there's any questions about this. Yes. Yeah. So I would not consider this to be subsetting because in our subset selection, we are explicitly thinking about some combination of x1, x2, x3, right? In our stepwise selection, we'll still end up with some of these guys. Okay, in a dimension reduction, you're going to end up with something more like this. Z1 and Z2, okay? And the Z1 isn't like one of these things. Z1 contains information about all three, okay? And same with Z2. Okay, so let me jump over to our studio. And hopefully we can elucidate this a little bit more. If we will do this. All right. And I also, okay, we're going to start off with a couple packages that we need to get to. So data table we have, ggplot we have, and then you guys should have ISLR from last time. And we're also going to need, I believe it's this one, PLS. Okay. Okay, last time we looked at a data set called credit. Now we're going to look at a data set called hitters. This is also coming from the ISLR package, so you don't need to download an extra, CSV data set or anything. We can load it directly once you have ISLR run. And line 6 is loading in that data. And line 7, I'm just doing complete cases, which is going to get rid of all the NAs. Let me take a quick look at what's in this data set. This is a baseball data set of player statistics. So each row represents a specific player, and then it has a bunch of stats related to their performance in baseball games. And what we're going to do here is attempt to essentially run some regressions. Specifically, I'm going to do a sort of dimension reduction technique where I want to look at how salary may be related to their performances. Okay. So we're going to run principal components regression. So that's what PCR stands for. So in this case, we'll have salary regressed on everything else, okay? And then what's coming from the hitters data set, usually you're gonna have some kind of scaling. And the reason for that is you can imagine that if this is in one kind of unit and this is in a different kind of unit, right? So in this case, let's just say, for example, this is your, what is the metric for, no, the average hit rate, is that the RBI? Anyways, it's like, suppose this is a number between 0 and 1, right? It's like a percentage of some, or a fraction of something it's getting measured. I think that's the RBI. I'm not a baseball guy. And then this might be like number of home runs. So if this is on the scale of like, in the sort of tens units, and then this is in the 0 to 1s, right? That's going to artificially make the sort of variance favored towards the scale that's bigger, which is why we have this thing called scale equals true that kind of just scales everything to be in the same range of values. And then this will do cross-validation automatically for you. And so why are we doing cross-validation? Here, I need to be able to figure out how many components there to have in my regression. Okay, in this data set, we have number of columns. Okay, so we're going to end up with our one explanatory variable and 19, or sorry, one response variable and 19 explanatory variables. Okay, so that means I could have one z here, I could have two z's, three z's, all the way up to 18 possible z's. Okay, and the more z's that we include, then the more essentially data that we're capturing out of my x's to explain my y's. So the model will continue to perform better and better on the trained data, but as you include more z's, you also start overfitting, right? And so by specifying validation equals CV, we're basically saying perform a cross-validation and get me the correct number of z's, right? Assign the right value of m in order to reduce your out of sample mean squared error to the best extent possible. So we're going to end up with some number of components between 1 and 18. Okay. So I've run this, and let's look at the summary of PCR fits. So let me go all the way up here. Okay, so let's kind of go through this and see what this is saying. So we have 263 players, 19 explanatory variables, my one response variable, and then it's going to do cross-validation using actually the root of the mean squared error. And these are going to be your cross-validation and adjusted cross-validation, I guess, root mean squared error values. And let's see what's happening here. So you typically want the lowest value out of your cross-validation. And so if we look just up here, we can see for cross-validation, our lowest value is just with, or sorry, this is our highest value. And we're looking essentially for the lowest cross-validation value. And I believe, so the top one is going to be in sample, and this one, I believe, should be out of sample. Let me see if that's right. Oh, no, sorry. Okay, my bad. So this is, all of this is actually going to be in sample. We're going to show, I'm going to show you how to do out of sample cross-validation in just a second. So generally, what we should be finding is that the cross-validation should continue to decrease, right? Because you're not doing any out of sample stuff. You're just doing cross-validation on the actual training set. So generally, the more components you have, the sort of better. So I can explicitly try and feed it an out of sample set of data. Let's look first, however, at validation plots. Mean squared error. And before that, let me see, does it actually have the, no. Yeah, okay, here, we can look at that. Okay. That is not what I was expecting. So, okay, so you can grab coefficients out of this model, which would refer to these thetas here. But unlike a linear regression, so these are still representing coefficients of your linear combination of your z's, but these coefficients don't really mean anything in the same way that a linear regression does, right? Because in a linear regression, it's talking about the relationship between your x's and your y's. Here, it's talking about your relationships between your z's and your y's. And the z's are just these like components of your x's. And so there isn't really a way to do any interpretation of the betas here, or in this case, the thetas. So then what's the point of doing this? Well, in this way, this sort of different technique, it's mainly focused on prediction. So you don't really care about the interpretability of these results. You mainly care about how this model is able to predict outcomes for your y. And so this is one of our first examples of how we're going to start straying away from linear regression, and one of the nice properties of linear regression about the interpretability. And as we go away from these assumptions about linearity, you start to get into these more complex models that have this trade-off about this interpretability aspect of your betas into things that like you can't really understand what these parameters mean, but that might give you better prediction outcomes. Okay, so this is kind of, I don't want to say a completely fundamental thing, but this is a pretty common pattern that we see, is that one of the trade-offs that you make for interpretability in more complex models is loss of interpretability to gain more predictive power. Okay. So that's kind of what's going on here. So let me look at this. This is a plot of your mean squared error as you have more and more components. And what you can really kind of easily see here, right, is that as soon as you add a couple components, which basically sucks in all of them, so the sort of most essential aspects of your explanatory variables, your mean squared error doesn't really improve that much. Right? And so we might think somewhere this many components might be kind of the sort of best strategy. Okay, so what I'm going to do is split the data set in half. So I'm just going to sample true and false We're going to do that a number of times equal to the number of rows for hitters. And then our test set is going to be anything that wasn't selected here. So your train and test are going to be a vector of true and false values that are completely opposite to one another. And we'll have X as model matrix from salary hitters like this. This is the same kind of thing that we did last time to set up the model matrix in our credits data set. And now we're going to have a second y dot test, represented as our y's, but then a subset of those from the true and falses that we had generated. Okay. So this time, we'll do something like this. We'll repeat what we had before. But now we're going to add an extra argument into this function where we have this subset train. Which is going to take in a vector of true and falses to run your PCR on. So it's only going to do a subset of the data. And we'll look at the same things that we did in our first one. All right, and let's see what happens. Okay, good. So in the first validation plot, kind of what we expect to see is this, if you guys remember from our bias versus variance. The first one is really kind of just doing this, and now we should have the combined effect of total error because we're doing the out of sample. So whereas in the first plot, we see something like this going continuously down, here we can see that as you add more and more, you're starting to experience overfitting, and your mean squared error starts going up as there's more components being added. And we should be able to see that in the summary. Okay, and so if I look at the cross-validation, we can see the mean squared error sort of increases as you add more components after, say, 1 or 2 of your first, actually after, I guess the lowest is 5 and 9, essentially. Yeah, and so after that, your mean squared error starts to jump up. Okay. So that is your PCR. Yes. Oh, yeah. Yeah, these should be different because we went through a sampling procedure. So anytime we do random draws here, so my line 14, you can expect that there's going to be a sort of slight difference. Yeah, was it different there too? What might be different about that? Well, it's doing cross-validation, so there's internal sampling happening as well in the function. So there should be some marginal differences. Even if these values aren't exactly the same, generally, I would think that we should be getting a similar final result in that the plot might look something like that, and that your optimal number of components is probably between the 5 to 9 range. Is that what you guys are finding? No? Maybe? Your plot is very different? Oh, you're saying it's starting to go up already? Yeah. So in this data set, it might be the case that certain actual like rows specifically have a big effect, which means like certain players in the hitters data set might be driving a lot of the outcomes. And so in the random sampling, if you happen to hit those players, yeah, maybe that's why. But your mean squared errors in your plot really shouldn't look too different from this. Okay. Did you have a question? No, okay. Yeah, and so that kind of covers the last sort of set of sort of selection, regularization methods, right? So this is sort of quite different from what we talked about in the stepwise, but this is a common type of technique in certain fields where you are sort of more concerned about your prediction than about interpretation of your coefficients. And this kind of guarantees oftentimes that you're going to do better predictive wise than anything you could get out of your linear regression, right? Because it's literally extracting all the information out of here. And if you go at the worst that could do, you could actually have your m equal to your k, which means that at the very least, this could be the same as a linear regression. And you would get essentially the same predictive ability as a linear regression. If it turns out that the relationship truly is linear, it could essentially sort of get to the same outcome. All right, any questions, confusions about this before we move on? The PCA is essentially the technique of identifying the sort of variance without doing the regression part of it. So it's the principal components. So it's figuring out the transformation of your x's to your z's. Yes, yes. We'll stop sharing. Okay. Okay, we are going to change topics now. So we've kind of finished talking about our different techniques that we can do to essentially deal with lots of variables. It's these three broad sets of things: subset selection, shrinkage, dimension reduction, and all of these things are sort of fairly, or I've shown common methods amongst each of these categories that help handle sort of many variables. Okay. So here we're going to change pace a little bit. We are going to be talking about logistic regression. Okay. So let me frame this a little bit. So we've talked so far about our regular old regression here. And we started out with this. Okay. And then the next thing that we sort of looked at, or then not the next thing, but we also then talked about what happens if X is a discrete value. And the way that we handle this, right, is by having X be represented as a categorical variable. And you can have this as a binary, right, as a 0 or 1, or a broader set of which the binary is a subset of categorical, which is sort of more than 0 and 1, right? Okay, so maybe you guys can guess what we're going to look at next. What happens if our y is discrete? And this is where we're going to get a little bit tricky here, and we're going to depart a little bit more from our sort of regular old linear regression. And so as we look at this, we're first going to start in binary, and then we'll think about what it means to be sort of having more than just sort of two possible outcomes. So we're going to look at y equals 0 and 1 first, and then we'll look at 0, 1, 2, 3. And when I say 0, 1, 2, 3, that doesn't mean a continuous thing. It's like number of different possible outcomes, okay? So you could think of this as like the outcomes of y might be heads or tails, which we could represent as a 0, 1. Or the outcome of y might be rock, paper, scissors, okay, which you might represent as kind of 1, 2, 3, but it's going to be not strictly like those numbers, right? So in a logistic regression, this is kind of the simplest way we can handle categorical variables. This is a regression model where the response variable is categorical. So again, our simplest example is going to be for binary outcomes, and then we'll extend this to multiple outcomes. So for this is going to be known as a multinomial logistic regression. Also known as an M and L. When you are sort of predicting on a categorical outcome, this is kind of just for nomenclature's sake. In traditional machine learning, they call this a form of classification. So classification is just doing essentially regression on categorical variables. But they decided to call it something fancy. And so logistic regression is one method of classification. So generically speaking, we'll have some kind of input into a model. And then this could be a binary outcome. Okay. So an example of this might be like income, education, race. And these might go into a decision to, let's say, buy a car. And then you have yes or no. So in a linear regression, your outcome takes on like a whole possible range of values. Here, we take on just 2 possible values. But sometimes you might find it useful, right, to represent this a little bit differently, where instead of saying just this outcome or just this outcome, this might be what you're guessing for like a single individual. But if you're looking sort of in aggregate across like a population, you might say, okay, X% says yes, Y. And this is right pretty different from the linear regression types of outcomes, right, which just are these types of things. We have some ability to look at different ways of slicing these sort of outcomes. So we'll keep that in mind as we kind of move forward. Okay, so conceptually, I think this isn't too complicated to understand, right? But how the heck do I measure like yes or no's in my Y's? So in a linear regression, I have my Y here and my X here. And I have a bunch of points, okay? And so on and so forth. And I draw a line. Great, we've talked about this. We kind of know how this works. We should know how this works. Okay, now we have something a little different. Y is 0, Y is 1. We only have 2 possible outcomes. Okay, we have something like this, right? You have different values of X, but you only have 2 values of Y. So X's have some kind of range of stuff, and then maybe you observe something like this. Okay. So if you have a categorical variable and your y's are just zeros and ones and you plug it into a linear regression, you'll get something like this, right? I don't know what this means. It's kind of meaning, well, okay, technically this, some people actually do this type of thing. And you count like stuff in here as like the probability that you have 0 or 1, and then you ignore the lines kind of going out that way, right? But fundamentally, there's probably something not quite right about this, right? I'm basically saying that if I did it this way, my y's could take on values in between 0 and 1. They could take on values going all the way to infinity and to negative infinity. It doesn't really make sense, okay? So in this case, what we have is something that is linear. And represents probability between 0 and 1, but is unbounded, okay? So my values down here can go down to negative infinity, and my values up here can go up to positive infinity, which is not what we want. So how can we modify this y equals beta x to try and fit the context of what we're trying to do? So one thing is that you can do, so y is equal to, let's say, the log, oops, log of, let's say, the probability of x. Okay. So this multiplies inputs together. But unbounded in one direction. So if you log the values, what happens to this kind of curve here? Actually, let me draw that first. You end up getting something that looks like this. So we're essentially trying to do transformations on my x's and possibly on the y's in some way to alter this curve. And the first kind of trick that people came up with is something like this. So probability and odds, and you end up with a curve that looks like this. And your odds, the odds are equal to the probability of a particular outcome. So this is success, and this is failure. Okay, so we're basically modifying our our inputs to do something like this. But the big takeaway here is that you are doing some transformations on your x's to get this kind of plot. And what you can see here is that you are now bounded in one direction. Okay. Here your odds can only go down to 0, but they can go up to infinity. Okay. So the last thing you can do is you can try and do a log of the odds. So this is log of p of x over 1 minus p of x is equal to my beta plus. So I've not only transformed this into the odds, I've transformed it into the log odds. And this will actually constrain, because if you have something like odds versus log odds, your graph will look something like this. So here our odds go from 0 to infinity. And here our log odds can go from negative infinity to infinity. So this is allowing us to essentially go into a sort of linear form here that's now allowed to go from negative infinity to infinity. So essentially what we've done is manipulate our data in such a way that that I can now go back to kind of running this sort of linear regression type of equation. But now my y's kind of look funky, okay? And this right here, this is known as your logit, okay? And that's what you're ultimately going to do your sort of logistic regression on. We have information about the probability of your x's. That's kind of related to your y values. And so if I want to solve for, if I want to solve for my p of x, you can do the math and end up with something that looks like this. And this is known as your inverse logit. And let's take a look at this in a sort of generic example. so that we can kind of digest the sort of theoretical aspect of going from y equals beta x into this sort of log p of x 1 minus p of x equals this, okay? This is the sort of mathematical justification behind why in a logistic regression, your regressions kind of look like these guys. And this is ultimately kind of what you're solving for in the regressions that we're going to be running, because we'll have our sort of y's, and then you solve for your betas in this equation. And then the interpretability comes back to these sort of transformations. So yeah, it's a little bit more complicated. We will get to multinomial in a little bit. But right now, let's just stick to 0 and 1. Okay, any other questions about this? The most important thing to know about this is that, okay, if you understand that like this doesn't really work, it's this, all of this is basically saying we gotta like solve this problem somehow. And it turns out that this is kind of the solution to dealing with this issue about having your y's go from infinity to negative infinity. We transform the y's to allow it to go from negative infinity to infinity.
Can you explain again what the probability means here?
That's the probability of a specific outcome given x. Okay, so that's this this like x% y% thing. So given some value for x, there's a corresponding probability that your y is equal to 1 or that your y is equal to 0. Make sense?
The probability when it's that's the 1.
Yes. Yes. So this odds is the type of transformation that we're making to let us do this, and it depends on p of x and 1 minus p of x. Let me show the example, and then maybe we can kind of digest more specifically what this means with like real numbers. Okay. Oh. Okay. There's a data set. I'm going to put it on Canvas right now, and you guys can download it. Sorry, I forgot to do this before class. Okay, we'll do this very quickly. This guy. We are in lecture 10. And Okay, they are now uploaded. So there are 4 CSV files, and we may or may not get to all of them today, but we'll be doing some of our examples using these guys. Okay. So the first data set, it's a pretty simple one. This is called election data. And this reads in this file called election_parsed, which is not here. Wait, what the heck just happened? Oh, I typed it in the console, sorry. Okay, election.data.read. I am probably not in the right directory. Yep. So I'll navigate over here, set this as my working directory, and try this again. Okay. Very simple data set, 2 columns. I think it said, yeah, a lot of observations, so 72,000 observations. What are these 2 columns? This is our Y variable, basically saying Democrats win or lose. If it's a 1, it means that they won in a particular area, and 0 means that they lost. And over here, this is our explanatory variable, which tells us the percentage of the population that are registered Democrats. Okay. So you can probably imagine what's going to happen. It's a pretty straightforward thing, but let's take a look. So we are going to use a function called GLM. GLM is a sort of higher family of the LM function. LM stands for linear model. GLM stands for generalized linear model. And so we can see in this case, technically it's still a linear combination of your explanatory variables. So it's still a linear model, but you're doing some kind of transformations to the data. And so the GLM can kind of help do this for you. We're going to talk after we kind of branch out and look at a couple different models. We'll come back and talk about the GLM in a later lecture, and sort of all the families of things that it covers. So this last bit here, family equals binomial, is kind of the critical thing that's that we need to include to kind of indicate that we're essentially going to be doing this logistic regression. Okay. I did a summary of it and looks familiar. We have coefficient estimates. We have for our intercept and percent dem. So who can help interpret this for me? Anyone? Yes.
As the number of, like the percent of Democrats, it increases by 1 million,
Yeah.
and the chances of Democrats winning election increase by, goes up by 40%.
Not quite. Because remember, our regression now looks like this. Okay. So it's a lot less straightforward. What does this mean? I don't know what the heck this means. It's okay, as the percent dem increases by 1, your log of your odds ratio increases by 48.3, whatever the heck that means. Okay. Let me do a manual version of this. So we are currently stuck in this space of working with log odds. That's what this is saying. Kind of the most that I'm going to be able to tell you. So I'm now kind of speaking generally. When I do a logistic regression and I see coefficients and all of these metrics, I can tell you that, okay, as the percent Democrats go up, then my outcome increases, right? So my ones will probably be more likely. And so percent Democrats goes up, the chances of Democrats winning is positively correlated with that. Okay, pretty obvious. And I'm just getting that from the sign of this thing. And then I can say, the standard error is really small, right? The probability is very high, or the p-value is very high. So I'm pretty confident that this is like doing something in the model. Other than that, I'm not going to have too much else to say about it. Okay, that's working in the what we're calling again the log odds space. We can also do some back transformations to get back into the probability space. And I'm always going to recommend that that you guys do this. So let me demonstrate the sort of math that we're doing here manually, and then we'll see essentially how to take our results here and make them a little bit more useful. Okay. So let me stop my screen share. And we'll keep this guy up on the board while I do this manual calculation. So probability perspective. Beta 0 is equal to negative 23.8798. Beta 1 is equal to 48.2926. Okay. So I'm going to use this equation here, the sort of inverse, and solve for here. So we're going to have something like exp of the quantity negative 23.8798 plus 48.2926. So this is where it's a little bit trickier, because in the old version, in our regular linear regression, the amount that your y changes, how should I put it? Okay, so remember this thing where we have a delta x. Okay, x changes by 1 unit, y will always change by beta. Okay, in this transformation, this is no longer true. As your x, if the x changes by, if x changes by 1, the change in my y, in the probability of y, is also going to be related to the level of x. So in other words, in this particular example, if my x is at 0.5 and I go up to 0.6, so an increase of 0.1, the change in my probability of x outcome will be different than if I go from x equals 0.7 up to 0.8. Okay, so that change is no longer linear. So let's just take an example here. Let's say I'm going to have my x level be 0.4. So this will be equal to 0.010325. Okay. So again, interpretation of this, my x changes by some amounts and something happens to the log odds. I don't really know how to interpret that. Let's look at this type of interpretation. If 40% of my population is Democrats, or registered Democrats, the probability that they win the election is about 1%. Okay. So you have to do a little bit more work here, but I think this is more clearly interpretable than that. Yes.
How much, like, what did you just say?
Yeah.
Percent of the population would all increase by 1%.
Okay. So Okay, so do you get, so I'm going to talk about the change thing in just a second, but if you understand this part, so I'm basically plugging in 0.4 for X, right? And just, yeah, arbitrarily. Okay, so 40% of Democrats, and you have a 1% chance of winning. So let me ask you, what do you think happens if I increase this by 0.1? So X goes to 0.5 here. In the context of this problem, what do you think the outcome might look like? Yeah, but like generally, like if there's 50% Democrats, 50% Republicans, what do you think the probability that Democrats win would be? Close to 50-50, right? Yeah, that's pretty logical, right? So okay, at 40% Dems, you have 1% chance of winning. Okay. I don't know if the 50% thing is exact, but I would assume it's close, and we can look at it in just a second. But let's say at 50% Democrats, 50% chance of winning. Okay. So my point earlier is that in a linear regression, every step that I take affects my Y outcome the same amount. But that can't be true here, right? Because if this is the same type of thing, okay, then that means that 60% Democrats, I have a 99% chance of winning, right? But at 70% chance, or 70% Democrats, am I going to have a 148% chance? No, right? This is just going to be like 99.99% or something, right? That's all I meant to say here earlier, is that now as I take a step in the X direction, my Y won't always change by the same amount. It depends where I started when I took that step. Yeah, by doing this. And you can do this many times and automatically actually in R, as I'll show. So to kind of reiterate, essentially what I'm doing here is like, we can display the results this way. This is the standard set of results that you're getting out of your regression, but we can also display our results this way. And to me, working in the probability space makes much more sense. Like we understand what's happening here. We don't really, I mean, I kind of understand, but not really. I've been doing this a long time and I still don't, like, no one really does these kind of interpretations of like coefficients of log odds. It's just too cumbersome. Okay. So let me do a practical showing of how to get these things out of here. Yeah. Yeah, you can have that. I'll show some examples of that. Yeah. It actually doesn't make it much more complicated. If X is discrete, it's like, so now you don't do this, you just have like two outcomes. So you have one probability happening at one thing and one probability happening at another thing. So what I'm gonna do now, I've kind of calibrated my model, I've gotten the results. I wanna do this thing here. And I wanna do this many times over the range of values that I'm interested in. So let me just go ahead and make that. So election.data.new. I'm going to make a data frame, or let me do it as a data table actually, just so I'll be consistent with everything else, equals sequence so I'm making a vector here of x values, and I'm making those x values go from 0 to 1 in increments of 0.01. Okay. So this should look familiar to folks. I'm using the predict function, and I'm plugging in all of these new x values going from 0 to 1. And then, so that's the new data. And then I have a type equals response. And type equals response just means the thing that I want to predict is these probability outcomes. There are other options here that you can do under type. And I think the default gives you the log odds here. So you could get the range of like log odds predicted outcomes. But again, that space is weird to work in. So we're going to focus on doing type equals response, which gets the probability values. Great. And now I'm going to plot this. And hopefully this will all come together for you guys. All right. Run this. So what I'm going to kind of advocate here is that as opposed to our regression table with the beta coefficients for your log odds, this is kind of the new representation of that. And what does this show? This is the typical shape that you're going to see coming out of logistic regressions. It's this kind of S-shaped thing, right? And this shows the probability of my two outcomes. My probability here is 0, or sorry, my outcome, this line is showing the probability referring to specifically one outcome, and that outcome is whether or not the Democrat wins. Okay. And so when you don't have a lot of registered Democrats, the probability that the Democrat wins is really low and increases, right, very rapidly as you go up. And so this is what I mean. So now you have a nonlinear change in what happens to the probability of the outcome depending on where you are on this plot. There's actually, if you think about the context of this problem, there's actually two lines, but we don't show both of them. And why is that? What is the other line? Yes, exactly. This is representing the outcome equal to 1. There's another one that would look like this. Like that. Okay? And that is the exact opposite. That's indicating the probability that the Democrat loses. That's the 0 outcome. And that line is the exact inverse of this. At any x value along this axis, right, in those two lines, you have two probabilities being represented. One probability for them winning, one probability for them losing. What is the direct relationship between those? Yeah. Yeah, exactly. So the sum of those two lines will always equal 1. That's why you don't show the other one. And that will come into play when we think about a multinomial logistic regression. You're going to have multiple lines. If you have 4 outcomes, you'll have 3 lines where you have, a bunch of S-shaped curves that look like this. And the last line isn't shown because it's 1 minus the sum of the other 3 lines. And so, okay, I'm trying to get us to think about that as a sort of preview for when we talk about multinomial logistic regression. Okay. So yeah, hopefully everyone understands kind of what this plot is showing. If you have any questions or confusions about it, now's a good time to ask. We're gonna work with a lot of this stuff pretty soon. Okay. Yeah, and again, in my opinion, looking at these probability plots and working in this space is just like infinitely more digestible than those coefficients we were looking at before, right? So yeah, if the choice is between displaying my results like this versus like this, right, I'm going to prefer the plot every time. I have a pretty good idea of what the plot is telling me. And I think it's providing a little bit more information than just the sort of coefficients. Okay. Okay. This is a good stopping point for today. We will move on to thinking about multinomial logistic regression, where we have more than 2 outcomes for y, more than 2 discrete outcomes for y next time. Yeah, and so make sure the homeworks are due today, right? Make sure to get those in, and then the proposals are due tomorrow. Lots of work, get it done. I'll see you guys next week. One sec.